Okay, picture this. You have to park a skyscraper in the middle of a stormy ocean. And not just park it, but hold it perfectly still, maybe just a few feet away from a multi-billion-dollar oil platform. Sounds completely impossible, doesn't it? Well, it's not. Welcome to the incredible world of dynamic positioning. I mean, really think about that. This is the massive challenge that engineers have been wrestling with for decades. Whether you're drilling for oil thousands of feet down, carefully laying a subsea cable, or supporting a team of divers deep underwater, staying in one precise spot without dropping a single anchor is everything. So how in the world do they pull it off?
Well, first things first, you have to know your enemy. And out at sea, any ship is in a constant, non-stop fight with three huge forces: the relentless wind, totally unpredictable waves, and incredibly powerful currents. These things never, ever take a break.
To win this fight, modern ships are armed with a true technological marvel. It's a system that acts like the central nervous system, the very brains of the entire boat. It's called a dynamic positioning system, or DP for short.
At its heart, a DP system is exactly what it sounds like: a really smart computer that uses the ship's own propellers and thrusters to stay put. It's a continuous loop of commands designed to perfectly cancel out those environmental forces. But trust me, that simple definition hides a staggering amount of complexity.
The whole thing works like a constant, high-speed conversation. First, the system has to sense where it is with pinpoint accuracy. Next, the computer has to compute exactly how the wind, waves, and current are trying to shove it around, and then figure out the perfect countermove. And finally, it tells the thrusters to act. This entire loop happens again and again and again, every single second.
So how does it sense its position? With an absolutely amazing array of high-tech gear. It uses satellite systems that are way more powerful than the GPS in your phone. It uses acoustic beacons on the seafloor, literally talking to the ship with sonar. It can even bounce lasers and radar off nearby platforms, or, get this, use a physical taut wire that's just connected to a heavyweight sitting on the seabed. By using a bunch of these at the same time, it makes sure it never loses track of where it is.
Okay, so holding your position is one thing. That's impressive enough. But what happens if something breaks? A thruster fails, a generator goes down. This is where the real genius of dynamic positioning comes in, planning for literally every possible failure. You see, the whole philosophy is built around one word: redundancy. The system is designed from the ground up to handle losing a thruster, or a generator, or even one of its computers, all without losing its grip on that one spot in the ocean. It's all about designing a system that can fail safely.
And the foundational document for this entire safety-first mindset is something called the Failure Modes and Effects Analysis, or FMEA. You can think of it as this massive book of what-ifs. It's an incredibly detailed study that looks at every single part of the system, down to the smallest component, and asks a simple question: what happens if this breaks?
And don't just take my word for it. The Marine Technology Society, the group that writes the guidelines for all this stuff, says the FMEA is, and I quote, the most important technical document on the entire vessel. It is the absolute Bible of DP safety.
The level of detail in one of these is just immense. Every potential problem they find is sorted into categories. A Category A finding, that's a showstopper. It means a single failure could be worse than what the ship was designed for, and it has to be fixed, period. This super rigorous process makes sure every single risk is known and managed.
And this isn't a one-and-done kind of deal. Nope, the actual physical tests to prove that the FMEA's conclusions are correct, they have to be repeated at least every 5 years. That way, you know the ship's safety plan is always current, even as the equipment gets older. So, with all this planning done, the crew on the bridge has to make a really important decision about how to set up the ship for whatever they're doing that day. And this brings us to a tale of two different operating modes. You could call them maximum safety versus good enough.
On one side, you have what's called critical activity mode, or CAM. This is the default, the gold standard. It's maximum safety where everything is set up for full redundancy. On the other side, you've got task appropriate mode, or TAM. Now, this is a conscious, deliberate decision to operate with less backup, maybe for a situation where losing position for a minute isn't the end of the world.
But let me be super clear. Choosing to operate in TAM is not a casual decision. The guidelines are crystal clear. You are required to conduct a detailed risk analysis. You have to prove on paper that the consequences of something going wrong are acceptable for the specific task you're doing.
And all this technology, all this planning, it all builds to the most important component in the entire system, the human in command. Because for all its incredible automation, the system is nothing without highly skilled people at the controls. They are the final backstop when things really go wrong.
The requirements for the crew during these critical jobs are incredibly strict. You have to have at least 2 certified dynamic positioning operators on the bridge, and one of them must have at least 3 years of experience on similar vessels. This isn't a job for rookies and demands real-world expertise.
And why is that experience so vital? Because when a truly bizarre failure happens, the automation might not be enough. A skilled DPO has to be able to instantly recognize that a thruster is acting up and shut it down, or deselect a faulty wind sensor before it literally drives the ship off its spot. Their quick thinking is the ultimate layer of safety.
Now, these rigorous standards we've been walking through didn't just appear out of thin air. They're the result of decades of experience, all compiled into guidelines by experts like the Dynamic Positioning Committee of the Marine Technology Society. It's this shared knowledge that makes these amazing operations possible and safe. So, in the end, dynamic positioning is this stunning partnership, this incredible dance between a machine and a human that lets us do things that honestly feel like science fiction. But it leaves us with a really crucial question, doesn't it? In a world where technology can do more and more for us, how do we make sure that the humans in charge are always ready for that one critical moment when the automation just isn't enough?